Hello, and welcome to the first video exploring problems on Wiley Plus. Today we're going to be going over the first problem on homework from week 1 of Physics 131. So the first problem we have here is an object has a charge of negative 4.6 microcoulombs. How many electrons must be removed so that the charge becomes positive 4.1 microcoulombs? So since we're trying to find the amount of electrons that must be removed so that the charge goes from being negative 4.6 microcoulombs to positive 4.1 microcoulombs, first I want to explain that we have the unit microcoulombs, which is the prefix micro, which is that little U looking thing at the beginning of the problem, translates to 10 to the negative 6. So then if we have 1 coulomb, let me write that down, 1 coulomb will equal to 1 times 10 to the negative 6 microcoulombs. So, wait, that was a typo, sorry. 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. So the SI unit for charge is coulomb, so we know that we're working with an amount of static charge. And from the previous physics class, I learned to use the equation delta Q equals Q final minus Q initial. The equation is used within the unit of thermodynamics, and Q is a standard variable used for heat energy. However, it could also be used for electric charge when talking about electromagnetism, which in this case, we are talking about that, and our SI unit would be coulombs, which is seen as a capital C. So with this in mind, I decided to use this equation to solve this problem. So let's get started with this problem. I'm going to just move this to the side so that we have this. Okay. So the first thing I did was I rewrote my equation one more time, just because I'm a visual learner, so that helps me. So again, we have delta Q equals QF minus QI, Q final minus Q initial. So first of all, I want to turn the microcoulombs into coulombs to make it easier for us to work through this problem. And the reason why we're doing that is because it's easier to turn coulombs, or to extract the number of electrons from coulombs. And right now we have microcoulombs. So we're going to start with our negative 4.6 microcoulombs. And then again, since we know from this equation here, or conversion I should say, we know that negative 4.6 microcoulombs is equal to negative 4.6 coulombs times 10 to the negative 6. And this is because we're multiplying by the 1 times 10 to the negative 6 to get us this. And then we're going to go ahead and do the same for the positive 4.1 microcoulombs equals 4.1, don't forget the positive charge, coulombs times 10 to the negative 6. So now that we have both of these in our unit of coulombs, we're going to go ahead and input them into our equation to find delta Q. So delta Q, our final, we have the positive 4.1 because we want to know how many electrons need to be removed from this amount to get this. So this is our final, this is our initial. So we have positive 4.1 times 10 to the negative 6 coulombs, and then we're going to subtract it by the negative charge, so don't get that mixed up. Oh, I accidentally wrote micro. Times 10 to the negative 6 coulombs. And then once we have this, we're going to plug it into our calculator. I couldn't find a way to project my calculator, so take this time to plug it in on your own. And then we should get 0.87. And then I like to have it in scientific notation, so 1, 2, 3, 4, 5, 6. That's where our new point is going to be. So really it's 8.7 times 10 to the negative 6 coulombs. Notice how we ended with this unit, and that's exactly what we want for this next step. So now that we have that, I'm going to write it over here, 8.7 times 10 to the negative 6 coulombs. We remember from a few lessons ago in this first unit of physics that we have 1 coulomb is equal to 1.602 times 10 to the negative 19th electrons, and that's per coulomb. So what we're going to do here is divide this number so that by the amount of electrons in 1 coulomb, so that we can get the amount of electrons in this amount of coulombs here. Okay, so divide by 1.62 times 10 to the negative 19, and this is electrons per coulomb, and we're going to cancel those out so that we're only left with the electrons. And then this is going to equal 5.43 times 10 to the 13th. You could check that, plug it into the calculator. But then this is what we're left with. So then let's go back to the question and make sure we answered it. How many electrons must be removed so that the charge becomes a positive? So we got this many electrons need to be removed from our initial, which is 4.6 microcoulombs, to get to our new 4.1 microcoulombs. And remember, it's going from negative charge to a positive charge. But I hope this makes sense. I guess to recap one more time, we're first converting these values above to coulombs by multiplying by 1 times 10 to the negative 6, which gets us our new values. These are in coulombs. And then plugging into our delta Q equation, we have our final minus our initial. And then getting these values here, and ultimately dividing them by our conversion here that we learned previously to get the amount of electrons left. So 5.43 times 10 to the negative 13, excuse me, it's 5.43 times 10 to the 13th electrons are needed to be removed from negative 4.6 microcoulombs to get the positive 4.1 microcoulombs. I hope this helped, and let's go to our next problem in this set. All right, so for the following problem, we have 4 identical metal spheres have charges of Qa negative 8 microcoulombs, Qb negative 2 microcoulombs, Qc is positive 5 microcoulombs, and Qd is positive 12 microcoulombs. 2 of these spheres are brought together so they touch, and when they are separated, which spheres are they if the charge on each one is 5? Okay, so starting off, we know that our total charge is going to be equal this. So we know that each sphere has, or needs to have, positive 5 charge of microcoulombs, and then since there's 2 spheres, we're going to go ahead and multiply by that, and that results in a positive 10 microcoulombs. So with that said, I have our 4 spheres over here. This is Qa, Qb, Qc, and Qd with their charges. And so, as we've learned in class, if we have 2 objects that are in contact, then some electrons will be transferred from one to the other, depending on which object is attracting those electrons and which object is giving up those electrons. So with that being said, we know that any of these 4 spheres are going to come in contact. We just don't know which ones. So given that we need a 10 charge, we're going to go ahead and add up the charges to see which ones work. So automatically the negative 2 charge and the positive 12 come to my attention. So we're going to go ahead and add Qb plus Qd. So Qb is, we have negative 2 microcoulombs and then plus 12, it's positive microcoulombs, and perfect, that results in our positive 10. And then we're going to divide this by 2 spheres to double check it, and that results in a positive 5 microcoulombs, and that's exactly what we wanted. So the answer to this question is the spheres B and D. In a similar manner, which 3 spheres are brought together and then separated if the final charge on each of the 3 is positive 3 microcoulombs? So again, we're going to separate our total charge. We know that each sphere is going to have a positive 3 charge, and then there's 3 spheres this time. So that results in a positive 9 microcoulombs. So our goal here is to then test the combinations of the 3 spheres that we have. So I can see that A and C might add up well nicely together, and then D is also another one. So if we have, for example, negative A, the sphere A is negative 8 microcoulombs. We're going to add that to the positive 5 charge that we have from sphere C, and then the positive 12 charge from sphere D. And then if you plug that into your calculator, we have 17 here, and then minus the 8 gives us 9 positive charge, and then divided by 3 spheres, that equals a positive 3 microcoulombs for each of the spheres. So our answer here would be spheres A, C, and D. And then going to our final problem, we have the final charge on each of the 3 separated spheres in part B is positive 3 microcoulombs. How many electrons would have to be added to one of these spheres to make it electrically neutral? So we know that our previous problem gave us the positive 3 microcoulombs. And then what we do here is we want to change them to coulombs just so that it's easier for us to then go to the next step. So as we remember, we have 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. So we're going to go ahead and just multiply this by 1 times 10 to the 6. So that results in 1.3 times 10 to the negative 6 coulombs. Perfect. And this will help us with this next step because, as we remember, one electron has a charge of 1.602 times 10 to the negative 19th coulombs. So in order to understand how many electrons we have to add to the sphere to make it neutral, we're going to divide by this, because that's coulombs per electron. So these cancel out. And then if we plug that into our calculator, we get this N2, because as you remember from the lessons, N stands for the number of electrons, which is what we're trying to find. So that results in 1.87, I rounded it up here, times 10 to the 13th electrons. Expand the decimal. And then we are left with this as our answer, electrons. And then also a note here is electrons are no non-units. So that's our answer, and then we're going to go ahead and check it. And it all checks out.